So like I said, we're going to be talking about temperature, composition, phase diagrams today. And the neat thing about these phase diagrams is this is also the introduction into distillation. And so what's actually happening with fractional distillation and how we get petroleum products from crude oil and all of those kinds of things, separating petroleum gases like propane and so on. All of that's related to these TX phase diagrams. So we're comparing now the PX phase diagram, which we just drew with Routh's law, etc., to the TX phase diagram. So let's focus on the left for now. This is the pressure composition phase diagram. Remember that XA and YA are tracking two different things. XA is the mole fraction of the liquid, and YA is the mole fraction of the gas or the vapor, those mixtures. And the interesting thing is that they're not the same. So at a given pressure, so we see right here at this given pressure, if we were to take this liquid that has a mole fraction XA and come up here and boil it, it's boiling because this is 1 atmosphere, so it's boiling. The vapor that's coming out of those bubbles has this composition, YA. Also looking at this phase diagram, what do you have at high pressure? You're going to have the liquid. What do you have at low pressure? You're going to have the vapor. Okay, so in the PX phase diagram, liquid's on top, vapor's on bottom. Now let's flip the axis and go to the temperature phase diagram. So this is not just flipping the pressure axis, it's just the phases flip. But now this is at a given pressure. What are the different boiling temperatures? So if we pick 1 atmosphere, that's going to be the boiling point. When the pressure of the mixture is, vapor pressure is 1 atmosphere, then it's boiling. And so these are the boiling points of the liquid. So the liquid phase is down here on the bottom. Low temperature would give you a liquid. High temperature would give you a vapor. So in all these cases with phase diagrams, look at the extremes. Just like the PT diagram, we looked at high temperature, low pressure, we've got a gas. Low temperature, high pressure, we have a solid. In between the solid and the gas is going to be the liquid. So just go to the extremes and do the same thing on this diagram. What do you have at high pressure? You got a liquid. What do you have at low pressure? A vapor. What do you have at a high temperature? You have a vapor. When you have a low temperature, you have a liquid. So don't get those swapped up. Okay. So now we have this solution at XA. Okay. This is the boiling point. It's roughly room temperature, right? 300 or 298 Kelvin. And this would be the composition of the vapor phase, YA. Okay. So you come up, when it boils, the vapor that leaves those bubbles comes over here, and it has this composition. And so this allows us to separate. If we take the vapor and let it go somewhere else before it condenses, then we've separated, we've enriched it in A. Okay? And that's how distillation works. So you boil a liquid and the vapor's enriched in the lower boiling substance, the lower boiling point. And so if you separate that, which you can, because vapor, remember, think about gases. Gases fill the whole volume of a container. So if your container is shaped like a distillation flask, those vapors are going to get up there. Now, we actually aid condensation by putting a cold water jacket on it, but you didn't have to. It would just start cooling as it got further and further away from the heat source, and then it would eventually condense. Actually, some of the chemical symbols that we see on, I think it's like the Boy Scout chemistry merit badge. It has this shaped flask on it. Looks kind of like a sigma. But that is a retort. That is a distillation, simple distillation. So this right here is a simple distillation apparatus. And so you have the liquid in here, you boil it, you put it on a ring stand. Back in the old days, they used Bunsen burners, even for organic solutions. crazy. So you're boiling the liquid, and as it gets farther away from the heat source and surrounded by air, it starts to condense, and then it drips over here in your collection. And so these were old-timey blown glass. They'd blow a cone, and then they'd bend that neck over and make these little retorts so they could distill. Modern-day distillation equipment is a little more fancy. And so here I've got a picture of one. So this is a fractional distillation column. And I've taken this picture with my infrared camera. It's a little FLIR infrared camera that fits on an iPhone. And so you charge it up. It's really an awesome thing. So I got the distillation running, and it started, you get the stable temperature gradient, hot down at the bottom, cold at the top, and it condenses and drips over. And so it's kind of like this old-timey retort, but with a longer fractional distillation column. So let's look at some of the terminology that we have in distillation. We have the condensate temperature. Let me just check, make sure the video is still going after swapping things. Okay, yes, just making sure. So this distillation terminology, you have the condensate temperature. So that thermometer up at the top is measuring the temperature of the condensate. Okay, and the condensate is then dripped out by the condenser into your collection flask. Okay, so that term, the condensate, is what's being distilled. In other words, also you could call it the distillate. Okay. Then you have the fractioning column. We'll get into a lot of detail on the fractioning column today. And then the still bottom or the pot. And so that's really important to know the difference between the distillate or the condensate and the still bottom in the pot. Okay, so we're going to make a lot of judgments using TX phase diagrams as to what ends up in the pot and what ends up in the condensate or the collection flask. And then the pot boiling temperature is higher than the condensate temperature. You have this temperature gradient. And so I actually took some measurements with this FLIR infrared camera. So you can point that little crosshair. You see it's pointed at the cooling tubes, and it's measuring 74.6 degrees Fahrenheit. So that's the cooling water that's running through the condenser. You can point it at the pot and measure the temperature of the pot. And so these different distillation steps in the fractioning column are evaporations and condensations. So if we're separating liquids by distillation, let's say we have this composition that's mostly A, but it's got some B in it. But B has a really low boiling point. So this would be TB for pure B, and this is TB, T boiling for pure A. And so this has some intermediate boiling point because it's a mixture of B and A. And so this mixture boils here. And then that vapor goes up the column a little bit and condenses. And when it condenses, it becomes a liquid that has this composition. Then it drips or runs down that fractioning column, which is a temperature gradient. And so it warms up again and starts to evaporate again. Well, when this liquid boils or evaporates, it has this vapor composition. And then that moves a little further up the column and then recondenses, and then moves up further, recondenses. And so here's just 3 steps. Here's one that has 5 steps. So you can have a bunch of different steps in your distillation going up that column. The taller the column, the more steps you have. Okay, and the longer the temperature gradient. And so let's compare these multiple steps to this column. Down here at the still bottom, 128 degrees Fahrenheit. This is what the infrared camera was measuring. And that is the temperature right there. Okay, so that's down at the still bottom. And then you have all these condensations going on. So you might have, 1 here, 1, 2, 3, 4, and 5 as they go up. So it condenses and then re-evaporates, and condenses and re-evaporates, and condenses and re-evaporates. And each time it goes to the vapor phase is more enriched in the lowest boiling component. And so eventually almost pure B reaches the condensate thermometer and then the condenser and is collected. So up here, the temperature using my infrared thermometer was 105 degrees Fahrenheit. And that is this temperature way over there, that last condensate temperature, which is very close to the boiling point of B. So this is how fractional distillation works, and we can see it in this TX phase diagram. Let me pause there for questions. Just trying to connect this to what you did in organic chemistry and real-world applications. Yes?
What was the chain for?
The chain, okay, it provides thermal mass. So think about the heat capacity for that bulky metal. It also prevents air currents. So you might have a burst, kind of like, I think of it as a sunspot. You know how the sun just erupts this blast of ions or whatever that comes straight off the sun. That's not really what's going on in the pod. It's not a fusion reactor, but still, you might have a burst of vapor that creates a current and a wind that goes right up the column. And this is to stop that wind. Okay, so you don't want a windy column or you'll get too much A over. Yeah, so you want it to be a tortured path up that column. And that will also set up a really good temperature gradient. So glass beads, chain, any inert material. A steel chain is pretty inert. Okay, sometimes copper was used, but copper is not that inert. It might react with some of the things, especially ammonia or amines will react with copper. So it's typically some stainless steel or glass bead object. It takes longer to distill the smaller the spaces naturally because you've got to get your materials up there. So our steel chain is cheap and it doesn't clog the column too much. Glass beads would clog the column quite a bit. You could get the same separation in a shorter column with glass beads, just because it takes longer for the vapors to get through the glass beads. Yeah. Good question. Anyone else? Let's take this same picture now and look at a refinery. Okay, this is what's going on in a refinery fractioning column. And so we talked about theoretical plates. Maybe you've heard that. When I heard in instrumental, when I was taking instrumental, they talked about theoretical plates for like gas chromatography, and the theoretical plates were 50,000 theoretical plates. The height of a theoretical plate was a few microns. Does this ring a bell? No? I'm seeing heads are shaking now. Okay. That's sad. Okay, in gas chromatography, the ability to separate two very similar compounds, okay, is you calculate the resolution of the column in that method, and the ability to separate two similar compounds. Think about the ability of a fractioning column to do that. It might be really tall if the compounds were very similar, like butane and isobutane. Okay, same mass, essentially the same boiling point. Very difficult to separate those two. You would need a 30-meter column, okay, in GC. I don't know how you could do it with a traditional bubble plate distillation column, but the old fractioning columns used bubble plates, and that's what's being shown in this diagram. And so they could calculate the height of a bubble plate and how many bubble plates you need to, say, separate diesel from gasoline. And so this engineering term of plates in your fractioning column was the term that they used. Mathematically, they applied that same terminology to gas chromatography. And so the height of the bubble plate, and that's a theoretical plate because in this glass column that's 30 meters long, there are no little plates. So they're theoretical plates. But in a gas chromatography separation, you might have 50,000 theoretical plates. It would be like a refinery with 50,000 bubble plates. You could not do that. Okay, it would be ridiculous engineering-wise. Okay, I can't say you can't, but it wouldn't be worth it. Okay. Now, and then the height. If you're going to put those into a finite length, like 30 meters, what's the height? Well, it's 50,000 theoretical plates divided by the length of 30 meters, and so then you calculate the height of a theoretical plate, and that would be sort of the height of the bubble plate you would have if you're cramming them all into 30 meters. Okay, so those are the terminologies that we use in gas chromatography. And I asked a question in class, and I'm still bitter about it to today, right? And I said, what is this plate business that they're talking about? And he said, well, it refers to bubble plates, and nobody uses those anymore. Okay, and so that's what my professor told me. Fast forward, got my doctorate, I'm in teaching at West Texas A&M, I'm president of the American Chemical Society, we have speakers come through, and this guy comes through and he's talking about refineries and so on, and he's talking about bubble plates. And I said, wait a second, bubble plates? I said, my professor told me that we don't use those anymore. And he said, your professor doesn't know what he's talking about, because that's what's here in this thing.
Yeah. Wow.
Yeah, every one of those fractioning columns uses bubble plates, and here's a bubble plate. We do use them. We don't use them in analytical chemistry at the university. We use them at the refinery down in Texas City, Baytown, etc. Okay, and so bubble plates are used. I was bitter that my professor had never been off campus and didn't know that we actually use bubble plates still. That's how we separate all of our gasoline and diesel and kerosene and white gas and liquid propane, etc. So here's the bubble cap. Here's the little vent that's inside the bubble cap. And every one of these little bumps is an individual bubble cap. And these little vents on the bubble cap are below the level of the liquid. So the vapor has to come up. So it's a bit under pressure because it's evaporated. It's hot. And so this liquid is boiled. And that pressure pushes it through, and it's in intimate contact with the liquid. And if it still has a higher vapor pressure than that liquid, it will continue to go up. But if it doesn't, it will condense. And so in this huge fractioning column, we have these bubble plates. And so you eventually get boiling points, like the boiling point of kerosene, and you could just pull a tap off of that. And then gasoline, a little lower boiling point, you have gasoline fraction. Down below kerosene, you'd have diesel, and the boiling point of diesel. And below that, really heavy oils. And so you just boil all of these, and you have taps that come off, and you collect the fractions. And so that's why you don't have a pure substance for gasoline or kerosene, because it's just a fraction. It's all of those compounds mixed together that have a range of boiling points. And so we just collect them at these different locations. And so at this refinery, we have the fractioning tower, okay? And then we have this maintenance and sampling platforms, okay? And then we have this fraction tap. So this pipe is coming right out of the middle of that fractioning tower, and it's pulling some product off. I don't know what refinery this is. I just pulled it off of pexels.com. It's a free photo site. But whatever the fraction is at this point in the column is coming off and collected and maybe filtered or whatever. But it's been distilled, so it's probably pretty good stuff. And then we have this hot to cold temperature gradient. So the heating source is way down here. So you heat up the crude oil, and then the lighter fractions move higher and higher and higher until even out the top you have propane, butane, pentane, all of these things that are going to have really low boiling points. Pentane boils below body temperature, so like you can hold a vial of pentane and watch it boil away. So that's why they do a lot of extractions with pentane, because it's so easy to boil off. But it's also very flammable, so you're generating a lot of pentane gas that if you have an open flame, you're going to not like it. So now you know what's going on in these fractioning columns. Still at the bottom, I would say, even now at the bottom, this is the still bottom. And all the heavy stuff and the dirt and the whatever else was trapped in that crude oil is down here at the bottom. And it's called the residuum or residual. And it just, if you think about that crude oil, you evaporate all of the solventy stuff, you're left with this tar. And even the tar can dry out and just leave you with charcoal. It's called coke.
I think those
Yeah.
could be used for the road construction.
Yes, and so you take that heavy asphalt base, which is down here at the bottom, and you take that and mix it with rocks and spread it out on the road because it's water repellent. And so you could just spread that asphalt base out and drive on it. Okay. And then you have the industrial fuel, things that can burn really dirty fuels. Okay, things that don't have pistons, so you can. There's a huge amount of energy content because it's mostly carbon, very little hydrogen, And so you saw from your QSAR lab or QSPR lab that the more carbon you have, the better the fuel.
Yeah.
The hydrogen is okay, but the carbon really gives you a boost. And so this stuff is, a lot of double bonds, a lot of heavy aromatics, very little hydrogen, a lot of energy per gram. You have all of these different catalysts that try to get more of the rich fuels up here. These things are expensive. Gasoline, jet fuel, diesel, that's where the money is made. And so if you can take some of these heavier oils and add hydrogen to them and hydrogenate these double bonds, you make a lighter fraction, you make something with a lower boiling point, you can sell it for more money. Wilkinson's catalyst changed the production of gasoline versus diesel by just a few percent, and it was worth billions of dollars. Yeah. So he's an inorganic chemist and won the Nobel Prize for his catalyst using, I think it was rhodium. It's this organometallic compound that hydrogenates these double bonds. Yeah. What was that?
I need to talk about the catalyst in his class, so I remember this one.
Yeah. So it's fantastic. Then the coker, you go in and this dry stuff, then they can go in and they drill it out. Sometimes you'll see at a refinery, you'll see this tower. It looks like oil derricks on top, and it's just drills that drill and pulverize this coke, and they sell it for, again, a fuel content, powdered fuel. So that's all of the products. Now these are just the fuels that we get. We take these also and maybe purify them more and use them as precursors for all of our plastics. So every plastic article that you're looking at right now came from this. So that's all of our plastics. Those are non-fuel uses for the fossil fuels. They're not just fuels, mostly fuels, but all of the plastics come from these different kinds of extracts as well. Now, let's add one little unit of complexity to the TX phase diagram. Some liquids will have the same composition of vapor and liquid. So whenever the vapor and liquid, somewhere in between, a mixture, have the same composition, so YA equals XA, that means there's a pinch in this vapor-liquid equilibrium line. So let me go back to one that doesn't have a pinch. Let me just back up a few spaces. Okay, let's look at that one. Notice over here on the left is pure A, and over here on the right is pure B, and nowhere in between is the YA equal to XA. It may help if I go all the way to the beginning. Let's look at this first one, where they're labeled. See, the vapor phase is in red, and that's YA, and black is XA. And nowhere in between are those values the same. But if you have a non-ideal mixture, they can pinch. And so if this boiling point of the liquid is not intermediate between the boiling points of A and B, like say it has a maximum or a minimum somewhere in between, then you're going to have what we call an azeotrope, where YA and XA equal to each other. Let's shoot forward. Okay, so here we have this phase diagram. Temperature on the y-axis. The blue curve is the vapor composition. The black curve is the boiling point of the liquids. So that's XA is the black line, YA is the blue line. And notice up here, XA and YA equal each other. And that point right there would designate what we call an azeotrope. And azeotropes are not separable by fractional distillation. That's the real take-home message. But if you look at this, it's very similar to just two phase diagrams. So you could just draw this line right here, and that's the azeotrope. And so if I take a solution right here and I boil it, and I do fractional distillation, what's going to happen? I'm going to collect this. It's going to It's going to boil. The vapor is here. The vapor condenses. Stop. The vapor condenses, gives me a liquid, which then reboils, which then condenses. And so pure A is collected. The lowest temperature substance is collected in the collection flask. So this is the collected. So what happens to this composition here if I keep taking away A? It moves this direction, doesn't it? So the still bottom becomes enriched in the higher boiler. The still bottom gets enriched in the high boiling substance because the low boiling substance is being taken away. What does the boiling point of the still do? The boiling point of the still moves right up this black line. So you can monitor the still boiling point, and it's going to get higher and higher and higher and higher, and then it's going to plateau until you get the azeotrope. So the azeotrope is going to get stuck in the still, and you're going to boil off all the excess B, all the excess A in this particular diagram. Okay. What if I was on the left side of the azeotrope? If I'm over here, I have too much B. So I'm going to come up here and the excess B is going to come off. And my collection temperature will be here, and my collection flask will collect the low boiling B, and my pot will move uphill to the azeotrope. So the high boiler always ends up in the pot, and the low boiler always ends up in the collection flask. And which one's going to be collected depends upon which side of the azeotrope you're on. So the collection flask just rolls downhill to whatever the downhill spot is. So if I'm on the right side of this diagram, I've got too much A. I collect all the excess A, and the pot moves towards the azeotrope. If I'm on this side of the phase diagram, I have too much B. I collect pure B, and the pot moves to the azeotrope. This is called a high boiling azeotrope because the azeotrope has the highest boiling point on the whole chart. That's obvious, right? Is that obvious to everybody? High boiling azeotrope. Doesn't have to be a high boiler. It could be a low boiler. So on the right is a low boiling azeotrope. Now, an example of a low boiling azeotrope would be ethanol and water. This diagram's not to scale for ethanol and water, but anyway, it's a good example. So if I'm starting here at A1, try to find my pen. I'm at A1. I boil A1. Here's the boiling point of that mixture. And it's enriched in B, which comes down. So this is going to be in the collection flask. So we collect the low boiler. As always, this is going to be my collection temperature, okay? And my pot is going to be enriched in A because I'm boiling off some B, and so the pot's going to move up here. So the principle always applies that the collection flask has the low boiler, and the pot always moves towards the higher boiling temperature. Now you might say, well, this is a way to purify A because it's going to end up in the pot and be pure A. But you can't purify the pot. The pot contains all the things that don't evaporate too. So if there's any dirt or decomposed junk in this mixture, and with heating you're going to get decomposition, you're going to have a dirty pot no matter what. So you can't use the still bottom to collect pure A. That's just theoretically pure A. It's going to have things that got cooked, in the heating of the pot. And you can't collect pure B because you have an azeotrope that's a low boiler. So low boiling azeotropes, you can only collect the azeotrope. That's why you can't use distillation to separate ethanol from water, because it has a low boiling azeotrope. It will always contain a few percent water. I think it's 5% water because it's a low boiler.
That's why we always.
And so just take the TX phase diagram when you have an azeotrope and split it in half at the azeotropic point, and then you just have two independent TX diagrams. And you got to decide which one you're in. Like it? This is fun stuff. I like the TX diagram. Okay. All right, so look at all of that. I'll try to put some terms together with these to quiz you for this week's homework.